Video 59 of the master course, Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is vibrational and thermal averaging. In this section, we want to distinguish between diatomic molecules and polyatomic molecules, because for diatomic molecules, we can obtain vibrational wave functions numerically, because the vibrational problem for a diatomic molecule can be written in terms of just one variable, the internuclear distance. So we are dealing with a Hamiltonian in just one dimension. And this one-dimensional Hamiltonian is written up here. So here we have the kinetic energy part with the second derivative with respect to this one variable, which is the internuclear distance. This part comes from rotation, so we also include rotation. And then we have the potential energy, which is now not a surface, but potential energy radial function. And there are several programs around which can solve this equation numerically. So one obtains the vibrational wave function pointwise as a solution, and one can obtain the energies for different vibrational rotational states. In order to use this pointwise vibrational wave function, then in the integrals which we have from the clamped nucleus treatment, which means we have to integrate whatever property we're looking at as a function of the internuclear distance over these pointwise vibrational wave functions. And that means that we also need to know the properties. For example, if we want to calculate vibrational averaged polarizability, so we need to calculate the polarizability pointwise, meaning at many different internuclear distances. And the integration over this pointwise wave function then is basically just a sum over all the points where we know the vibrational wave functions, and then multiply it with the value of the property, in our case, for example, the polarizability, and then have to sum over this. And that will give us then the vibrational averaged polarizability. If you also want to calculate the vibrational contribution, the pure vibrational contribution to the polarizability, then remember, these includes transition moments over the electric dipole moment, transition moments with different vibrational wave functions. But from the numerical solution of this equation, we can not only obtain the vibrational wave function for the ground state, but also for excited states, all of them pointwise. But that also means in order to calculate this purely vibrational contribution to the polarizability, we need then the electric dipole moment as a function of the internuclear distance, also again pointwise. Now let's look at the more complicated case of polyatomic molecules. There what one normally does, so here's the averaged electric polarizability, so averaged over the nuclear wave functions. And what one normally does, one expresses this as the value of the polarizability at the equilibrium geometry plus a correction, which is the vibrational correction. One then expands the polarizability at an arbitrary for an arbitrary geometry in a power series expansion in the normal coordinates, where normal coordinates of the vibration, where here we have the equilibrium geometry value, and then we have the derivative with respect to all the normal coordinates, all the normal modes, times the normal mode. And that's a linear term, and then we have also a quadratic term where we have the second derivative of the polarizability times two normal coordinates. And in principle, one could continue, but in most applications, one actually stops here. Now, inserting this expansion of the polarizability at an arbitrary geometry in our expectation value up here. So we insert this up here, which means I get then integrals over the polarizability at the equilibrium geometry, but this is just a number, this is a value, which means I can take it out of the integral, and then I have the overlap here of the vibration wave function, but the vibration wave function is normalized, so I just get the equilibrium value out. And then I insert the next two terms, but the derivatives, they are evaluated at the equilibrium geometry. So they're also just numbers, so I can also take them out of the integrals. So what actually really remains in the integrals are the normal coordinates or product of the normal coordinates, which means the vibrational correction looks like this. So I have a sum over all the normal coordinates and the partial derivatives, first derivatives of my property here, the polarizability, and then integrals over one normal coordinate, in the next one a product of all kinds of products of normal coordinates. So in order to evaluate this vibration correction, I need to know all the partial derivatives of my property here, the polarizability, with respect to all the normal modes, the first derivative and the second derivative. And in most applications, one has actually to do that numerically again, to calculate them as numerical derivatives. And then I have to calculate here expectation values of a normal coordinate or product of two normal coordinates with a vibrational wave function. And let's look at this, how we get those vibrational wave functions. Which means we get them, of course, as the solution to the field free. So it's the unperturbed vibrational wave functions, no electric field perturbance. And they are found by solving the corresponding unperturbed vibrational Schrodinger equation, where here we have the kinetic energy for the nuclei, and we have the potential energy, which is the electronic energy evaluated for all kinds of geometries. And here's our vibration wave function. So we have to solve this Schrodinger equation. Now the potential energy, which is the electronic energy as a function of the geometry, that's also expanded in the Taylor series in the normal coordinates. So again, the electronic energy is the electronic energy at the equilibrium geometry, precisely as we did it for the polarizability. And then I have, in principle, I would have the first derivative with the normal coordinates, but evaluated at the equilibrium geometry, but the first derivative of the energy with respect to normal coordinates evaluated at the minimum geometry, that's zero, because it is a minimum. Otherwise, if it's not a minimum, it would not be zero, but we expand around the equilibrium geometry, which is a minimum on the potential energy surface, so the first derivative is zero. But we have the second derivative, and the second derivative right here in terms of the vibrational frequencies, because the vibrational frequencies are related to the second, essentially the second derivative of the energy. And the next term with three normal coords, here we have what is called a cubic force constant. Now you can see the harmonic vibrational frequencies, omega A, they are the square of what is called the harmonic force constants. And the harmonic force constants are the derivative of the energy, the second derivative of the energy with respect to two normal coordinates. And the cubic force constants are then the third derivatives of the energy with respect to normal coordinates. Now, if you would stop the expansion here after the second term, where we have the normal coordinate squared, that's the harmonic approximation. So we have an harmonic potential. And with this harmonic approximation, the Schrodinger equation for the vibration looks like this. Now all in normal coordinates. And we can write it, as one can see, we can write here the Hamilton operator as a sum over Hamiltonians for each normal mode, which means that we actually can, having written like this, we can separate it in a separate Schrodinger equation for each normal mode, because the Hamiltonian is a sum over terms which each of the terms only depends on one variable, which are here the normal coordinates. We can separate it in different Hamiltonians and different equations, one for each. So we get a one mode equation, one normal mode equation here. So our Hamiltonian is a sum, therefore here we have only one mode. And this is the one mode wave function. So that's just a wave function for one normal coordinate, one normal mode, and the total wave function is, because the Hamiltonian is the sum of terms, the total wave function is then the product of this one mode functions. And the energies here are then again, the energies are also sums of the energies for each vibration mode. And since it's sort of an harmonic, it's just a harmonic oscillator. So this is just a harmonic oscillator equation. And the energies are then for each normal mode, we get an energy expression, which is just again the harmonic oscillator energy expression. But for the total energy, because I have more modes, I have to sum over all those. That is the harmonic approximation. That is when we stop the expansion of the potential energy surface just after the quadratic term. But that is, of course, is a not very realistic approximation, so we have to at least go to the next term and include some unharmonicity. And the next term is cubic in the normal modes, and here we have the cubic force constancies. Now, the way one attacks this very often is by perturbation theory. So therefore, the treatment which I'm going to show you here is what is called vibrational perturbation theory, where this cubic term is our perturbation. The vibrational wave function then, the field-free vibrational wave function, are then expanded in the usual expansion of perturbation theory. We have the unperturbed wave function, that is the harmonic oscillator wave function as we had on the slide before, and then we get a first order correction. The double index up here and here tries to indicate that in a way we're dealing with double perturbation theory, because these are the vibrational wave functions which are not perturbed by the electric field. And these are now expanded in the perturbation, which is the unharmonicity in the potential. So the first, this zeroth order, that is still zeroth order in the electric field. And this one, the second zero, which is now 1 here, is then zeroth order or first order in the perturbation due to here the unharmonicity in the potential. Now, like normally in perturbation theory, we expand the first order correction again in a complete set of functions, which are all excited in some way or another. All these functions here are many mode wave functions. So they are product functions over harmonic oscillator wave functions for each of the normal modes, each of the normal coordinates. And excited means then that I can excite each one of them separately. Let's, for example, imagine that we are dealing with water. In water, we have 3 vibrations, so we have 3 normal modes. So this excited wave function could then, for example, be that the first vibrational mode is excited to one of the excited vibrational levels, and the other 2 wave functions are still in the ground state. But excited wave functions could also be that 2 of the vibrational wave functions are excited to different levels, excited levels, or all 3 of them could be excited. So there are many possibilities. Now in the following, we will look at what is called the 0-point vibrational correction, or abbreviated ZPVC, which means we will assume that the system is in the vibrational ground state. And therefore it's 0 point because for 0 Kelvin, then we are sure that the molecule will be just in the vibrational ground state. So it's basically the vibration correction at 0 Kelvin, therefore it's called 0-point vibration correction. And that, of course, also means that we are looking at corrections to the ground state vibrational wave function. The question is then, which of these many excited, unperturbed vibrational wave functions, product of harmonic oscillator wave functions, which of those can make a contribution to the first order correction to the ground state vibrational wave function? And luckily, it turns out that actually not so many, because only if one of the modes is excited, we actually get a contribution to this first order wave function, because we are looking at a correction to the ground state wave function. So in this set of functions, which is a product of one mode function, meaning harmonic oscillator wave function, then one of them is excited, whereas all the other product functions are not excited. Of course, we can vary then which normal mode is going to be excited. Furthermore, it turns out that the excitation is not an arbitrary excitation, but it's actually only excitation to the first excited vibrational state, which can make a contribution. I mean, all the other excited state wave functions are there, but if one insert them, their contribution is actually zero because the integrals become zero. That means that the sum over all the vibrational states actually is reduced to a sum over all the normal modes. And then we have here these functions, and they are then normal ground state harmonic oscillator wave functions. For all the other normal modes, then normal mode B, and for the normal mode B, we have the first excited harmonic oscillator wave function. So that's our set of functions, and then we have our perturbation operator, which is this term including the cubic force constants, and our unperturbed ground state wave function, which is the product of the harmonic oscillator wave functions for all the normal modes, but in the ground state. And divided by the energy difference, but the energy difference is that just actually only because harmonic oscillator wave function, or the energy difference between the ground state and excited state is h bar times the harmonic frequency, and we have only excited one mode, so mode B, so it's just h bar times the frequency of. So now we have to evaluate this integral up here. It's in a way, it's a transition moment because this is a ground state and this is an excited wave function. But we should remember that these are product wave functions, product of a harmonic oscillator wave function, and here we have the corresponding known modes. So in order to evaluate this integral B, we need some integrals over simple harmonic oscillator wave functions, different ones, ground and excited states, and with one normal mode, or with two normal modes, or with three normal modes. And these integrals you can look up in any decent book about vibration spectroscopy. Now, using these, what one of course then does is this integral here, which is an integral over normal modes, in the first place is split up in product of integrals over each normal mode, and then you can use this relation. And that's what you're going to do in one of the exercises. It then turns out to be that the integral which we have in the numerator of our first order correction to the wave function becomes this simple expression here, where here we have the cubic force constants and here we have two of the harmonic frequencies. So that the total first order correction to the wave function, first order correction to a ground state vibration wave function looks like this, where we still have here all our excited wave functions, and here we have the expansion coefficient, which was the integral divided by the vibration frequency, and that's the reason why it's omega b here becomes omega b to the third power. So that's our first order correction to the wave function. Now let's go back to the expression. If we go back to this expression here, we can see that an integral over a normal mode, single normal mode with harmonic oscillator wave functions is zero if we have the same wave function on both sides. The only case where it's not zero is if the two wave functions differ by one in the quantum numbers. The vibrational correction to the polarizability, in our case now the 0-point vibrational correction, so for 0 Kelvin. And we had two terms, so the expansion, we stopped the expansion after two terms, and the first one was with the first derivative of the polarizability with respect to normal modes, and then the integral over the one normal mode with the vibrational ground state wave function, and then the second derivative of the polarizability and the integral over a product of two. Now it implies then that if we just take the ground state harmonic oscillator wave function, which is the product of all the harmonic oscillator waveform for each mode, this integral is going to be zero. And therefore one evaluates this to first order, so one uses the first order wave function in here. in the bra or in the cat. Whereas the integral in the next term, that's the integral over the product of 2, and that is not 0. So the first order of vibration wave function which we have derived is actually going to be used here together with the first derivative where we have the second derivative of the property. We just evaluate the integral to 0th order. And doing that we get at the end this expression here where you can see here the contribution from the cubic force constant which comes from the first order vibrational wave function. And here's the expression. This integral here actually turns out to be essentially just h bar over 2 times 1 over the harmonic vibrational frequencies again. So the first term here we have, in the first term we have the first derivative of the polarizability, but we have the anomicity of the potential included, because that gives rise to the first order correction to the wave function. Whereas the second term is nonlinear in the polarizability, I mean it's the second derivative. However, we just use the harmonic potential in order to evaluate that term. For this reason, these two terms are sometimes called that this term includes mechanical anharmonic contributions because it's the anharmonic term from the potential, whereas this one would include the electrical anharmonic contribution because it's now a second derivative of our property. So this was the 0-point vibration correction, so it's 0 Kelvin. Now if you have higher temperatures than 0 Kelvin, then we will have not only the vibrational ground state occupied, but we will also have, to a certain fraction, the higher vibrational states occupied, and it's the Boltzmann distribution, which tells us how many and how much they are occupied. So we have to do a Boltzmann averaging on top of this in order to get the temperature dependence in, which means we will have to calculate this vibrationally averaged polarizability with the expression which we just used before for different vibrational states. And then we have to make a normal Boltzmann averaging where we here have the vibrational energies then. And then this can of course be done again with our expansion of the vibrationally average polarizability in terms of the value at the equilibrium geometry. And then we have to actually just Boltzmann average the vibrational corrections. Now for the vibrational polarizability, we need then vibrational energies. We need the vibrational energies, I mean not just the ground state vibrational energy, but many more vibrational energies, and we have to calculate vibrational transition moments. And these vibrational transition moments is basically vibrational averaging of the electric dipole moment, but we have here now two different vibrational wave functions, but we can use the same kind of perturbation theory approach as we have done for the averaging of the polarizability.